Hello everyone. My name is Haibin Zheng. I am a PhD candidate at Zhejiang University of Technology. The paper I will be presenting today is titled NeuronFair, Interpretable White Box Fairness Testing Through Biased Neuron Identification, which was done jointly by Zhejiang University and Huawei Singapore Research Institute. The first is the background. Nowadays, algorithms provide us with convenience, such as search engines, recommendation systems, recognition platforms, and so on. The issue of bias in the decision-making process cannot be ignored either. For example, in 2015, the image classifier used by Google Photos refers to a black woman as a gorilla. To avoid this problem, in 2018, Google simply dropped gorilla from the tags. The magazine Wired uploaded 40,000 animal pictures to Google Photos and then used keywords to search for pictures. After searching with keywords such as gorilla, chimp, chimpanzee, and monkey, it shows no results. When we tried to search for this picture, Google Lens showed that it is not clear. After several years, bias in decision-making still exists. In 2021, when we Googled soldier, it still showed mostly male-dominated images. Only when a female soldier is searched, women appear. Moreover, with the rapid development of deep learning and the rapid implementation of artificial intelligence applications, it is urgent to solve the problem of biased decision-making. Deep learning-based resume screening, crime prediction, and education assignment are all subject to biases based on gender, age, and race attributes. Several institutions are also committed to the realization of deep learning fairness, such as Microsoft, IBM, Google, etc. They released various debugging platforms. However, different platforms have their own debugging methods, and they also have their evaluation measurements after debugging. Completely different fairness evaluation results may be obtained for the same debugging method. Thus, it requires us to test their fairness, either for the original model or the debugged model. Before the launch, we all need to test the fairness of its decision-making to provide multiple guarantees. The existing fairness testing methods can be divided into three types according to the service objects. The first is testing methods for traditional machine learning. These methods cannot be applied to deep models. The second is methods for traditional machine learning, but can be applied to test DNNs after modification. The third is methods specifically designed for DNNs. For example, ADF uses gradients to speed up test instance generation. Based on ADF, IDIG uses momentum to accelerate convergence, further improving efficiency. These works are limited in practice due to at least one of the following reasons. These methods can hardly be generalized to unstructured data. The generation effectiveness of these methods is challenged by gradient vanishing. Almost all existing methods hardly provide interpretability. Then, we introduce the basic knowledge and our motivation. Here we give the basic knowledge about data form, discriminatory instance, and discrimination analysis based on decision boundary. The first is data form. Denote X as a normal dataset, and its instance pairs by X and X prime. For an instance, we denote its attributes by A, where S belongs to A is a set of sensitive attributes, and ANS is a set of non-sensitive attributes. The sensitive attributes, such as gender and race, are pre-given. Here we take the adult dataset as an example, which has 13-dimensional attributes, of which the gender attribute is marked in red, labeled as annual income or less than 50K or greater than 50K. The second is discriminatory instance determination. When the sensitive attribute changes, the prediction result of the instance pair also changes, which is expressed as a discriminatory instance. Here we take the 5-layer fully connected network model as an example. When the sensitive attributes are flipped, the annual income prediction results also change. The third is the discrimination analysis based on decision boundary. After changing the sensitive attribute, the decision boundary is crossed, and discrimination occurs at this time. It should be noted that the decision boundary is difficult to describe. Thus, based on the decision boundary, only discrimination can be analyzed, but cannot be interpreted. Then, we introduce the motivation. First, the decision results of DNNs are determined by the nonlinear combination of each neuron's activation state. Thus, we imagine whether the biased decisions are caused by some neurons. Secondly, we try to observe the neuron activation state in DNN's hidden layers through feeding instance pairs. Through this operation, we found that neurons with drastically varying activation values are overlapping for different instance pairs. Third, how to identify these sensitive neurons. We perform a hyperbolic tangent operation on the activation difference value to obtain tan active. Further, we found that its approximate optimal tan active value has a linear relationship with the sensitive neuron ratio, as shown in the figure. So we plan to draw the S-curve with tan active as the x-axis and SNUA as the y-axis, then use y equal to x as an auxiliary curve, and get the intersection of the two curves, which is the approximate optimal SNUA value. This operation makes the frequency of tan active appear normally distributed. These sensitive neurons are called biased neurons. Thus, our design goals and solutions are as follows. We intend to uncover and quantitatively interpret DNN's discrimination. Thus, we use biased neurons to interpret DNN's discrimination. Then, we plan to apply these interpretation results to guide fairness testing, so we take the biased neuron as the optimization object, and take the derivation from the biased neuron to shorten the derivation path. Third, we want to generalize our testing method to unstructured data, therefore, sensitive attributes are modified by adversarial attacks. To overcome the challenges, we propose an interpretable white box fairness testing, NeuronFair, which can generate more quantity and higher quality discriminatory instances. NeuronFair contains three main steps: quantitative discrimination interpretation, interpretation-based individual discriminatory instance generation, generalization framework on unstructured data. Here, we provide an example running on a 5-layer FCN model based on adult data. First, according to the previous definition, we draw the S-curve of each layer. Here is the 5-layer FCN, labeled as L1 to L5. Next, the layer with the largest AUC value is selected as the most biased layer for subsequent test instance generation. Here we selected the second layer with AUC value of 0.7513. Finally, we adaptively identified biased neurons by making auxiliary lines. Algorithm 1 shows the details of AS plotting and AUC calculation. The discriminatory instance generation includes a global phase and a local phase. Because the global phase is to increase the diversity of test instances, it is necessary to find more dissimilar original instances as seeds for global generation. For this reason, we cluster the original instances and randomly select them from each cluster. Next, we examine the discriminatory instances in the raw data, represented as solid red circles. Then, the global seeds are randomly selected from the remaining instances. The found discrimination by global search is represented as solid red hexagons. Repeating this operation for the remaining instances, we can obtain a diverse global test. Instance. Algorithm 2 shows the details of global generation phase. The discriminatory instances obtained in the global phase are used as seeds for the local phase. Similarly, we use an instance as a seed, then determine the search direction and then add perturbation. Repeat the operation for the remaining instances for local generation. Algorithm 3 shows the details of local generation phase. Step 3 is instance generation on unstructured data. Taking a phase detector as an example, we expect that the detection results will not change with sensitive attribute differences in the image. Modification of sensitive attributes on unstructured data is inconvenient. We draw on adversarial attack methods to design an adversarial testing framework. The framework is divided into 3 parts. The first is feature extractor based on convolution module. The second is face detector based on fully connected module. The third is sensitive attribute classifier based on fully connected module. We conduct adversarial attacks on the sensitive attribute classifiers to generate sensitive attribute perturbation. Then, following the previous steps, we adopt instance pairs to find biased neurons in the second module. For the face detector, the bias perturbation is generated according to the dynamic loss function. The generated instance pairs are then fed into the model. If the face detection result changes with different sensitive attributes, it is a discriminatory instance pair. In conclusion, our three steps can serve to implement an interpretable fairness testing method with reduced gradient vanishing probability that can be used for unstructured data. The experiments are introduced next, starting with the experimental setup. We evaluate NeuronFair on 7 datasets, of which 5 are structured datasets and 2 are image datasets. The image dataset is used for face detection, which consists of Solebe, LFW face dataset and ImageNet general dataset. For example, CLBIN dataset consists of 60,000 face images from Solebe and 60,000 non-face images from ImageNet. The pixel value of each image is normalized from 0 to 1. We implement 5 FCM-based classifiers for structured datasets and 2 CNN-based face detectors for image datasets. The FCM-based classifiers can be divided into 2 types. The one is composed of 5 hidden layers for processing low-dimensional data, denoted as LFCN. Another is composed of 8 hidden layers for processing high-dimensional data, denoted as HFCN. We implement and compare 4 state-of-the-art methods with NeuronFair to evaluate their performance, including ICSE, symbol generation, ADF, and IDIG. 5 aspects of NeuronFair are evaluated, including generation effectiveness, efficiency, interpretability, the utility of AUC metric, and generalization of NeuronFair. The generation success rate represents the proportion of discriminatory instances in the generated non-duplicate instances. Generative diversity represents the ratio of instance coverage. Fairness improvement represents the proportion of discriminatory instances in randomly generated instances for a debiocid model. Consistency represents the consistency between our proposed AUC metric and the traditional metric DMRS in terms of fairness evaluation. Significance is used to compare which metric can more discriminately identify decision biases in different models. We evaluate NeuronFair by answering 5 research questions. The first is, how effective is NeuronFair in generating discriminatory instances? When reporting the result, we focus on the following aspects: generation quantity and quality. NeuronFair generates more instances than baselines, especially for densely coded structured data. For instance, on adult dataset, the instance number of NeuronFair is 217,855 on average, which is 16.5 times and 1.6 times that of ICSE and IDIG, respectively. The outstanding performance of NeuronFair is mainly because the optimization object of NeuronFair takes into account the whole DNNs discrimination information through the biased neurons, while ICSE and IDIG only depend on the output layer. The instance number on Compass dataset is 11,232, which is slightly lower than that of IDIG. Since the Compass is encoded as 1 hot in AIF 360, we speculate the reason is that too sparse data coding reduces the derivation efficiency from biased neurons. NeuronFair generates significantly more test instances. From the table, we can see that the p-values for all models are small enough to reject the null hypothesis, which proves the significance of NeuronFair. NeuronFair generates much more instances than all baselines in the global phase, which is beneficial to increase the diversity of NeuronFair's instances in the subsequent local phase. For instance, on all datasets, the instances number of NeuronFair is 866 on average, which is 9.45 times and 1.42 times that of ICSE and IDIG, respectively. NeuronFair is robust to the hyperparameter tan active. The figure shows that different thresholds can obtain similar results. About the generation success rate. We can conclude that the GSR values of NeuronFair are higher than that of baselines on almost all datasets. The GSR value of NeuronFair on different sensitive attributes is more robust than ADF and IDIC. The valid input space of NeuronFair is larger than baselines in general. About the generation diversity. We can conclude that in all cases, NeuronFair can generate more diverse instances. There is a similar trend in the generation diversity for the same sensitive attribute. About the fairness improvement, we can conclude that, in all cases, NeuronFair can obtain larger DMRS values, that is, the instances generated by NeuronFair contribute more to the DNNs fairness improvement. This is a summary of the answer to the first question. The second question is how efficient is NeuronFair in generating instances? About the generation speed. NeuronFair is more efficient in generation speed. It produces instances with an average speedup of 534.56%. Next, how to interpret NeuronFair's utility by biased neurons. About the coverage of biased neurons. We can conclude that the main reason for NeuronFair's utility is that its instances can activate more biased neurons. NeuronFair's instances activate 100% biased neurons, while 62.5% for ADF and 75% for IDIC. Next, how useful is the AUC metric for measuring DNN's fairness? We can conclude that, in all cases, AUC can correctly distinguish DNN's fairness violations. In all cases, AUC can distinguish the different DNNs discrimination more significantly than DMRS. The computational complexity of AUC is much lower than that of DMRS. This is a summary of the answer to the fourth question. The final question is how generic is NeuronFair for the task of image instance generation? About the instance number in global phase. In all cases, NeuronFair can obtain more instances than ADF and IDIC, especially for the race attribute. About the generation success rate. Among image data, image instances of NeuronFair are of higher quality than those of ADF and IDIC. About the realistic of generated instances. The generated test instances are similar to the seed input. About the fairness improvement and the detection rate. We can conclude that NeuronFair contributes more to the fairness improvement of the face detector. NeuronFair hardly affects the detection rate while improving its fairness. This is a summary of the answer to the final question. In conclusion, proposed NeuronFair, an interpretable white box fairness testing method. NeuronFair performs well on interpretability, efficiency, and generalization. We conducted detailed experiments to evaluate the performance of NeuronFair on 7 real-world datasets. Finally, we systematically analyzed NeuronFair from 5 aspects. Thank you for your attention.